here's a result of some experiment of measuring 338 silver pennies of the pointed helmet type of synod. I don't know what that means, but anyway, it no someone measured the weight of some silver pennies, coins. Okay, and here are the ranges, intervals of weight. The weight is a continuous variable, so it can take any, usually positive values. It's not just integers. It can take some fractions, or in fact it's real numbers. Okay, so it's a continuous random variables, and within this range interval, so weight is between 10 and 11 grains. It's a unit of weight. So here it says 1 grain is equal to 64.79 something milligrams. So yeah, it's just another unit for measuring weights. So between 10 and 11 grains, there was 1 penny. Between 11 and 12 grains, there were 5 pennies. So here we have an interval of 1 grain, size of 1 grain, right? 1 grain, 1 grain, 1 grain. But here we have an interval between 14 and 14.5. In this interval, they found 15 pennies. Okay, so the interval can be of any size. It's arbitrary because it's continuous. So we could have used intervals like 10.10 to 10.15 and 10.15 to 10.56. It can be any intervals. These choices of numbers are just arbitrary. So that's one difficulty in dealing with continuous random variables. And we cannot define, we cannot count a number of pennies for exactly one value of weight, like weight of exactly 10 grains. There will be no pennies. If we measure the weight very accurately, there will be some deviation from exactly 10, right? There will always be some deviation. And also, there will be always some error in measurements anyway. So it doesn't make sense to count the number of pennies at exactly 1 point of weight. So we always have to consider some intervals. This is a must. We need to consider intervals. Okay, but the choice of interval sizes, this is arbitrary. So what do we do? So to understand how we deal with this, let's plot this data in a graph like this. So this is a histogram of these weights, and these the horizontal axis is the weight. Okay, as we have seen in this table, some intervals are of size of 1 grain, some intervals are size of 0.5 grains. Okay, so this plot should reflect those differences in the interval. Okay, let's see. Can you see? So this is an interval of 1 grain, 1 grain, 1 grain, 1 grain, but this is an interval of half grains. Here, half, 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 and 1. And actually this last interval is infinitely large. Look, here. greater than 19, greater than or equal to 19, up to infinity. But fortunately, unfortunately maybe, we didn't find any pennies of this size, of this weight. So we plot this like this. So we know why these widths are different. Okay. What about the height? So if we divide these numbers by the total number of pennies, do we get the height? Okay. For example, let's pick the largest number here, 65. So 65 divided by 338, what do you get? Let's see. What do you get? 65 divided by 338 is 0. So 65. This will correspond to 0.192. Okay. So what about the height? So the highest bar in this graph is this one, right? So that should be between 15.5 to 16. So that is this, yes. So that corresponds to this indeed. But what about the height? The height is above 0.35 and below 0.4, which is far greater than this value. So what's wrong? Actually, this height by itself doesn't mean anything. What this bar means is that the area of this bar corresponds to this number. Okay. So let's say the height of this is h, and the width of this is 0.5. So h times 0.5 should be equal to this number, 0.192. So the height should be 1.8 something. No, 0.38 something or so. So that is this number. See? And so when the width of an interval is 1, then still this area corresponds to these relative frequencies. Let's take this one. So 13 to 14. 30 to 14 is 22. So this should correspond to 0.0651 or so. Okay. So in this case, since the interval size is 1 grain, the height should be equal to this. So let's say, let's see. So this is about, yeah. So it's 0.05 is here, 0.1 is here. So yeah, this should be somewhere around 0.065 or so. See? So what matters here is the area under each bar. So even if you take smaller intervals, still the area should represent the relative frequencies. Okay? And if you add all this area, then it should add up to 1, right? Because if you add all these numbers and divide by the total number of coins, then it should be 1, right? So what matters is the area under the curve. So in other words, in order to define the probability distribution of continuous random variable, we need to always consider some density. Okay, so area under the curve divide by this width. Okay, so in the case of continuous random variables, we define something called probability density function. Okay, density. So if we define density function as functions that satisfies this equality. So this is the density function. Okay, this is the probability, right? So we have some sample space and we have real numbers. We have this random variable. Then we pick some subset, which is this interval. So from x1, not including x1, but including x2. Okay, so this is closed, this is open. Closed, open. Take this interval and find some corresponding subset of omega, which should belong to the sigma-algebra. Okay, so this is a shorthand for this subset of omega such that this random variable takes the value between these. Okay, omega. So again, I repeat, so this should be always an event. Okay, an event is a subset that belongs to the sigma-algebra. Okay, so this equation defines this function, which is called density. Okay, probability density function. Okay, so what we have seen in the plot of these coins, was a kind of approximation of the density function. Okay, so these values are the values of density function. Okay, so if you integrate this density function, that means you are calculating the area under the curve, right? So this area. If you integrate all possible values of random variables, then that should be equal to 1. Right? So if we integrate from negative infinity to positive infinity, this density function, it should be 1, because that interval from negative infinity to positive infinity includes all possible values of the random variable. So that should be the entire space, right? So all possible values should be entire space, entire sample space. So the probability of the entire sample space is 1. So this should hold. Okay. And the cumulative distribution function for the continuous random variable is, actually the definition is the same. the cumulative distribution function is the probability that the random variable takes the value less than or equal to the given value, which in this case is actually the integral from negative infinity to small x of f of x dx. So this is the cumulative distribution function for continuous random variable. Okay, let's see one simple example. Let's consider a density function. So x uniform density function. So this is A, this is B, and here's 0, and x 0. Okay, so this value is 1 over b minus a. So this is an example of a density function. So this is a uniform distribution between a and b. Okay, so this function is 1 over b minus a if x is between a and b. Otherwise, it's 0. Okay. By the way, for a random variable to be continuous, the sample space must be continuous, right? Continuous means uncountable. If the sample space is countable, there are at most countable number of values, possible values for a random variable, so it cannot be continuous. So what is this? Well, I mean it can be any sets, but usually we just consider real numbers as the sample space itself. Okay, in this case. So in that case, what is the sigma-algebra? Actually, we didn't explain this before, but and we are not going to explain this before here because it's beyond the scope of this module. But there is some standard type of sigma-algebra used for real numbers, which is called Borel sigma-algebra. So this is a sigma-algebra defined for real numbers. Okay, and so this is a collection of subsets of real numbers. So subsets in this case are like intervals like this between a and b, so a and b, so maybe half open, half closed, both open, and maybe one side is infinity, whatever. So this Borel sigma-algebra contains all such intervals. Of course, since this is a sigma-algebra, all complements of these intervals are also included. And also unions of all those intervals are included in this Borel sigma-algebra, because otherwise it will not satisfy the axioms of sigma-algebra, right? But anyway, just relax here and assume we have some nice sigma-algebra behind this scene. Okay, so here's an example of a density function, and so the probability in this case, if we want to calculate the probability that the random variable is between x1 and x2, we just integrate.